Alright, so this is the last lecture before we finish out chapter 19, talking about the ray nature of light and now applying it to real situations. Even though this is the last lecture for chapter 19, we still actually have 2 more class days to solve these problems, and we'll be talking about the history of optics as well in class. And so we have a couple more days to do these. I do want to remind you from the previous lecture that these homework problems still need to get done. And so if you haven't started these, I really encourage you to go ahead and start doing them at home, even though we have class time, because we'll spend that class time reviewing a lot of chapter 19. So please do go ahead and attempt some of these at home. We will have some class time, but maybe not enough for every single one of these. So I'm going to start out this lecture with a slight diversion about color, kind of why we see color, right? And so last week in lab, we discovered that a prism will refract light of different wavelengths at different angles. And well, what we were doing is we were using white light to shine into that prism. And the thing maybe you didn't know or didn't remember from high school or middle school is that white light is actually a combination of all wavelengths of light. We use the acronym ROY-GBV to understand this. The R is red, the O is orange, the Y is yellow, the G is green, the B is blue, the V is violet. It used to be ROY-GBIV, B-I-V. A few years ago, indigo got actually demoted as a color. It does not have its own specific wavelength. And so it's kind of an optical illusion that our eyes play on us. So we did ROY-GBV. In your book, table 19.1 is going to be really important. And it's going to be really important in problem solving because in some problems they'll say red light. And you need to know that red light has a wavelength of 650 nanometers. Or they'll say blue light, right? And you need to know that that's, well, about 450 nanometers, etc., etc. And so go ahead and find this table in your book, and you're going to want to either dog-ear that page or maybe just go ahead and copy this whole table onto your formula sheet. That would be a good choice. And so what I'm going to do now is take a slight diversion. It's very relevant to how optical things work, and it's also very relevant to your labs that you're doing in class, but there are technically not really any questions on this. So anyways, dispersion is this thing that we use to describe refracting light at different angles, and so this is actually what you did last week. In chapter 18, we said that the N is specific to a material. So like N for air, the refractive index for air is just 1. Or the refractive index for water is like 1.12, right? And in lab, we discovered that, well, that's not totally true. It also depends on the wavelength of light. And when we use white light, we are secretly using all of the wavelengths of light, right? And so as we send white light into a prism, what we find is that violet has a very high angle of refraction. It gets bent the most, while red doesn't have as big of an angle of refraction or as big of an index of refraction for this prism. And so this is actually what you did last week, and we figured out in blue, right, and red for the prism. This is why you see a rainbow, because of the different refractive indices of the different wavelengths of color. And again, it's just a little bit of review. Red and, let's see what I'll do. ROY, GB, V, so I'm at least kind of in the same order as this picture off to the left. Red has long wavelengths of light, all the way down to violet, which has very small wavelengths of light. Red also has a very low frequency wave. Violet has a very high frequency wave. And so on Friday this week, we'll do a physical demonstration of why things refract. When Isaac Newton was first studying light, he's the one that decided that white light has all of the colors, because what he did, it was well known in his time that a prism will separate out colors and you get you get a rainbow, you get Roy G. Biv, right? But Isaac Newton came up with this idea to figure out, okay, well, are all the colors added together white, or is white all of the colors, right? And so people didn't know the relationship between all the colors in white. And so what Isaac Newton did is he actually just took another prism to recombine all of these, and then he figured out that because of that, once they're combined, he gets white light again on the other side. So the actual relationship is that white light is made up of all of the different colors of white, right? This is why you see a rainbow, because things refract. You see a rainbow when it is misty outside, and every single little water drop in the air is acting like a prism. And so you know that when we shine light into our prism, it kind of bends and then goes out. Well, there are some angles too where some of that light starts to get reflected from the inside surface. And you saw this in your prism as well. So light gets reflected from this inside surface, and it actually comes out as Roy G. Biv, right? And so what you see is red coming from the rainbows high up in the clouds, and then green, right, middle of the spectrum, from these that are a little bit lower, and then blue from the ones that are even a little bit lower. And so what we see is that if we have a single rainbow, we see this. A double rainbow, which is double rainbows, a little more rare. Double rainbows actually reverse the color, and so you see, you'll actually see red. Red again, and then green, and then another blue. So a reverse rainbow, the second rainbow, is kind of doubled back, but all of it has to do with the angle at which these things approach your eye. So out of every raindrop, there is all the colors of the light coming out. It's just a matter of which ones hit your eye, and they happen to do so in this order. I'm going to also take this opportunity to answer the lifelong question, why is the sky blue? And I'll also talk about ocean creatures, which I promised you that I would in class. So in our visible light spectrum, right, long wavelength, short wavelength, low frequency, high frequency, and we've got little summaries here. This would also be a great thing to put on your formula sheet as just a quick check about wavelengths and frequencies of light. Red is readily scattered as part of, is the least scattered color in the spectrum. These higher wavelengths like blue and indigo and violet are the most readily scattered, and so what we see is that red can go very long distances through air without changing a whole lot. Whereas these blues and violets, as soon as they enter our atmosphere, they scatter. And so that's why we see the blue kind of color in the sky, while the sun appears this yellowish color, because again, that yellow color is able to travel farther and maintain its integrity than those shorter wavelength lights, those blue lights. Why are sunsets red is another good question. And well, sunsets are red, right? And so let's pretend that I've got a person standing here. Hope you can see them. The sun at high noon looks yellow, right? Because that's kind of where it's at. But the sun at a sunset is way off on the horizon. And so these rays have a lot longer, a lot more atmosphere to go through than they do at midday. And so the only colors that reach your eyes at this point are the reds. And if you kind of get a really excellent sunset, right, you can see reds, and then you see oranges and yellows. Maybe you even have a really good sunset and you get a little bit of green, and then turns into the blue and the violet on the sunset. And all that is refractive indices, as long as these rays are traveling through all the water droplets in the air, acting like individual prisms to give you, again, that Roy G. Biv, or just a nice red sunset if there's not a lot of stuff in the air. Right. I also want to talk about color absorption. So I just talked about color dispersion, which was kind of like light scattering as it hits these individual water drops, right? It kind of goes in all directions. So blue is most scattered, red is the least scattered. Color absorption is a little bit different though. Instead of just like a drop of water, when we get to the ocean or maybe a really deep lake or something like that, we see the opposite pattern happening. And that's because, well, those aren't being those aren't being refracted. The colors are actually being absorbed. And so what we see, and these are in meters, by the way, not feet. What we see as you go down in the ocean is that red and orange are one of the first colors to disappear. We can see yellows and greens a little bit better, and then we see blues all the way down here. So what we actually get is that when the sun shines, right, blue is the most predominant color that we see because, well, that's all that's available at these depths. And blue is primarily what's available at beyond 10 meters. So if you go diving on a reef, all of your pictures just look blue because, well, that's most of the light that's down there. There's not a whole lot of red, orange, or yellow. If you take a light down with you, however, right, if you take a light, you are actually emanating white light, right? And now what you've just done is you've become a source of all of the colors. And so within this, you've got red, orange, yellow, green, blue, and violet, R-O-Y, G, B, V. And so if you take a light down with you, you can actually see all of the colors. But without an artificial kind of white light source, blue is pretty much all you get. All right, so this is really interesting. Right, red disappears first. I'm just going to note that one more time. When I get down to the deep, deep, deep ocean, a lot of the creatures have things in common. And one of those things that they have in common is that a lot of them are red. And these creatures are red because at that depth, there is no red light. And as I showed you guys last week, if there is no red light, what color does the object appear? Well, it appears black, right? There is no red light to be reflected by this object, and so it just appears black, which is great in the deep ocean because, well, everything else around them is black. And so them having this red pigment is actually a defense or camouflage mechanism in the deep ocean. When we bring these creatures up and shine a white light on them, well, then they appear red, but that is not their natural habitat. All right, so back to resolution of optical instruments. That was a 13-minute diversion on color and dispersion and absorption. So an aberration is an imperfection in a lens. When we talk about resolution, by the way, we're really only talking about microscopes and telescopes. So things that are looking at very, very small things or things that are looking at very, very far away things. So typically not cameras. So within these optical instruments, microscopes and telescopes, there are what we call aberrations or imperfections in the lens. It could be that a lens isn't perfectly symmetrical on either side. Maybe there's a bump or a divot, or maybe it's been dropped or damaged in transport or something. Who knows? But we're humans, we don't make perfect lenses. So most lenses have aberrations. The other interesting thing is resolution is the ability to tell the difference between two objects that are very close together. And so your eyes actually have a resolving power, and you're probably familiar with this. So if you're driving somewhere at night and there's an oncoming car that's very far away, when it's very far away, well, it just looks like one light, right? You can't tell the two headlights apart, even though you know they're two objects that are just close together. But then as you get closer, you actually start to see two individual lights instead of just one light. And so what we say is that when objects are closer, you are better able to resolve them, right? You're better able to tell the difference between those two things. And so what we get with aberrations is that these rays don't actually converge, right? Not properly, not like we taught you they do, because there's some slight imperfections here. We also get different wavelengths of light focusing at different points. And so as you can imagine, this adds for blurry images and miscolored images through telescopes and microscopes. And so to fix this, what we do is we get achromatic doublets. And so in a microscope or a telescope, we've got these converging lenses to do the job that we wanted them to do. And then we actually put a diverging lens right behind it to kind of refract those dispersing rays in a way that focuses them nicely and neatly. So we have a very low power, high dispersion lens right behind it to kind of refocus everything, not only the rays, but the different wavelengths of light as well, so that we get a sharp picture with correct colors. Right? And so microscopes are a little more complicated than we've led you to believe. And so again, a good example is that if I'm driving when I am very far away, right? I know there's two headlights, but I might just see them as like one big light, right? Or maybe I start to see them as like these two blobby lights. But as I get closer, I can actually distinctly tell the difference between those two lights. And so at this point, I'm able to resolve. And well, the difference in that is the angular appearance of these. As I get closer, the angle between the two objects gets bigger, right? And so telescopes kind of have the same problem. So when I'm looking at two stars out in our galaxy, say, and they're kind of angularly close together, if I don't have a good telescope, well, I can't resolve those stars. They look like one. I might not be able to tell the difference. If I have a slightly better telescope, I might be barely just able to resolve them, right? And so this is starting to look like two stars, but not quite. And maybe if my eyes aren't good, I still can't totally resolve them. But at this point, we say that they are totally resolved, right? These stars, I can definitely tell the difference between them. And so telescopes have a minimum angle that they're able to resolve. And it depends on two things. It depends on the wavelength of light being received, and it depends on the diameter of the telescope lens. And so you guys know how fractions work, right? So let's say I've got a wavelength of 1, just to make things simple. If I have 1.22 over, let's say 2, versus 1.22 over 4, right? And these will be meters for diameter of meters. And you got to make sure to use meters for your wavelength. Which one is going to be the smaller number? Well, larger denominator means smaller number. And so what this means is that as the diameter of the lens of my telescope gets bigger, the angle that I am able to resolve things at gets smaller and smaller. And so small angle, very far away. When you think about this, this is the primary determining factor in the cost of a telescope. So the cost of a telescope is entirely dependent on how big it is, because how big it is entirely dependent on how good it is at seeing farther and farther out into the universe and being able to actually tell objects apart at great distances. And so while a home telescope might have a diameter of like 0.2 meters, and that's a pretty nice home telescope. An observatory, right, and so a place where you go and actually look at stars, might have a diameter of, like 10 meters or something huge, just in comparison. And so the bigger the diameter of the telescope, the better the telescope is at resolving or telling the difference between very far away objects that might appear close together, right? We're going to move on and talk about the resolution of a microscope. And so the resolution of a microscope is actually entirely dependent on what we call the numerical aperture. And we don't express this as an angular distance, but as a physical distance between two things, like two bacterial cells, right? And so the minimum distance that a microscope can resolve is this constant, 0.61, times the wavelength of light, and the smaller the wavelength, the better, divided by the numerical aperture. And the numerical aperture is posted on the lens, on the objective lens of a microscope. And so on the outside of a microscope, it might say something like 10x and then slash 0.95. The number after the magnification is the numerical aperture. And so we'll take a look in class and we'll play around with microscopes and figure out the resolving power of that microscope. Anything that is less than this minimum distance for that microscope, when you're looking through, you might only see one cell instead of two, right? And so these things can be misleading, which is why very powerful microscopes are very important to science. All right, your homework is on 634, numbers 33 through 35, and we will be playing with color and lenses in class along with microscopes, and we'll figure out the resolving power of our telescopes over in the Striegel building. Have fun, and I will see you in class.